Okay, good evening everybody. My name is Barry Broderick and I'm here to introduce this latest talk in sports technology in place of Garrod O'Line. These talks are hosted by Electrical and Electronic Engineering and of course Sports and Exercise Engineering program, which is the only program of its kind in the country. This particular talks are here to inform students on the potential applications of electronics in sports. The talks are sponsored by Engineers Ireland and the Institute of Electronic and Electrical Engineering. These talks are mainly for students, but they're also open to the public and just in a way to raise awareness of what sports and exercise engineering is about and what students can take away from this course. Today I'm delighted to introduce today's speaker is Dr. Gavin Corley. He's a colleague of mine. He's going to give a talk on Reengineering the Swimmer, the science and technology of swimming. Dr. Corley received his Bachelor of Engineering in Electronic Engineering in 2006 from the University of Limerick. He has then went on to obtain his PhD from the Bioelectronics Research Cluster from NUI Galway in 2010. He currently holds a position as adjunct lecturer and postdoctoral research fellow in NUI Galway. Gavin himself is a competitive swimmer, has been for most of his life, and he spends quite an amount of his time teaching swimming and coaching swimming. So I'll leave it up to Gavin.
Thank you. Thanks very much. So you're all very welcome. I suppose just kind of by way of my own introduction, as Barry said, I would have spent a lot of time swimming. My old coach is here as well, so I've got to be conscious about what we term competitive. I suppose as a youth swimmer, I would have done a lot of competitions at the kind of provincial and national level, but I wouldn't be by any great shakes, a massively successful competitive swimmer, but I would have spent a lot of time in the pool training. I'm also a qualified swimming instructor, so I spent the last 10 years kind of teaching adults and kids just starting to swim, so instruction as opposed to coaching. As Barry mentioned, I did my degree in electronic engineering, so really I learned to design and kind of build electronic devices, which is one of the main focuses of our discipline here. And then I did my PhD in the area of medical electronics, so I would have looked at kind of the anatomy and physiology, specifically for treating chronic illnesses. I would have looked at, say, physical activity in older people and ways that we can use a lot of the electronic technologies that are available now, say in your phone, to try and develop new treatments for them. So that's kind of a core focus of our research group. What I wanted to do today really is I was kind of conscious that over the last year or so I started doing a little bit more swimming. We're surrounded by technology in our lab and all of you I'm sure have smartphones. So I started to be very conscious that the gear I bring with me down to the pool kind of day to day these days is pretty much unchanged since when I started swimming however many years ago. So I was just curious to see how is it that a lot of the technologies that have developed in the last 10 or 15 years, how come they're not translating really into the pool as quickly as you'd imagine? So you see an awful lot of these fitness devices now for monitoring your speed and your heart rate, but we don't see it as commonly in the pool, particularly around real-time feedback and stroke metrics. So what this is really is, it's my take on some of the technologies that are emerging. It's not a comprehensive review of all new swimming technologies, but just a couple of select ones. And I'm conscious that we kind of have a swimming audience, an engineering audience, and some coaches as well. So hopefully you'll be able to take something away from it. So I'm going to talk just briefly about the background of swimming. I think there's probably a lot of you have been swimming for a number of years. I recognize a few faces. But for those of you that are new to it, just a very brief introduction to how important the sport it is. I'm going to talk about the physics of swimming, so kind of the nuts and bolts that any swimming instructor would be learning, which informs our stroke analysis. There's a couple of fundamental physical principles that we're interested in. And then the last half of the talk really is going to be on the technology of swimming. So the first two is kind of background. Okay, so in Ireland and the UK, more people swim, more adults swim than in any other sport. So I don't know if many of you realise that it's the most popular participation sport at the moment in Ireland and the UK. Now that would have changed, I think, maybe 2 or 3 years ago. There was a blip in that trend, but generally speaking, swimming is the most popular sport in the country at the moment in terms of participation. Not only do more people swim than do any other sport, but there's also a greater demand for swimming than any other sport. So in the UK, one thing that the Sports Council there looks at is latent demand for sports. So they have kind of an ongoing study on the activity of adults, and they do these telephone surveys in the order of 100,000 people every year, and they ask them, their level of participation in sports and what sports they'd like to become more involved in. And they asked people if they'd like to participate more often in sports. And the group, about a third of the people said that they would. And then they asked that group of people if they could pick one sport, what would it be? What would they like to do more often? And swimming, by far, 34% of people said that they'd like to swim more often out of that group. The next closest was cycling, which is 13%, and football, which is 10%. So swimming is popular, but there's also a massive demand. More people want to get into it. And I think if you're an instructor, you'll be keenly aware of that demand. So swimming is hugely important. And part of the reason that swimming is so popular, it's very therapeutic. I think anybody would tell you that. But it's good for your heart. There's a lot of evidence to suggest that it's good for your blood pressure. It's a whole body workout. So you have 4 different strokes. You're working a wide range of muscles. It's a low impact exercise, so it's suitable for athletes maybe with injuries, for older people who'd be a little bit more frail, perhaps. And it promotes joint flexibility as well. And in Ireland, where we've so many waterways, and although we don't spend as much time at the beach as we'd like, it's a fact of life that we're constantly surrounded by water. So swimming really is a fact of life. It's a necessary life skill, and it's an incredibly important sport. The other thing is that swimming is really exciting. So this is the last leg of the men's 4x200 meter relay in 2004, and Peter van der Kay is looking a little bit like Bugs Bunny. But that's kind of the anticipation that you commonly see at a large swimming meet. And again, if most of your swimmers, you'd be familiar with that. But I think it's a real shame that we don't have large arenas in this country that on a Sunday you look forward to go to see a swimming meet, rather than some of the other sports that we look at. But I think that's a whole other day's work. Okay, so the physics of swimming, right? So there's a couple of kind of fundamental principles that we look at if you're an instructor at even at a basic level or at a more advanced coaching level. There are a few basic principles that you want to be looking at in order to inform your stroke analysis. So the 4 main swimming forces that you'd be concerned with would be buoyancy, so that's the upthrust. You have the weight then, which is the downward force. You have your forward thrust, which is what you want to maximize, and then you have the drag, which slows you down. Okay, so you're probably all familiar with those terms. Essentially, in any competitive racing sport, what you want to do is you want to maximize thrust and minimize resistance or drag, and every swimmer is familiar with that. So buoyancy and balance. Okay, so the first thing I think I would have spent a lot of time teaching adults over the last 10 years who would have a big fear of the water. And the first point to call with them really is buoyancy and getting comfortable being buoyant. There's a big fear of falling. And a lot of the time what they don't realize is the water is working very, very hard. If you have a particular body density, it's working very, very hard to push you up all the time. So falling is the last thing you're going to do. And so I would have spent a lot of time trying to convince people of that. So where does this buoyancy force come from, and how does it influence your body position as you're swimming? Well, fluid pressure increases with depth. That's kind of a fact of life. Pressure is exerted equally in all directions, and because of these two things, what happens on a submerged body in the water, a submerged baby in this case, is that the forces that the fluid exerts on the top of the baby are a lot less than those underneath, because those forces are coming from a greater depth. So you get a net upward force, which you call the buoyancy force, and I'm sure you're all familiar with it. Archimedes' principle says that the weight of the volume of displaced water is equal to the magnitude of that buoyancy force. And what that means is that when you pop something in the water, it's displacing an equal volume of water. Okay, now before you displace that water, it was perfectly balanced between its weight and the buoyancy force. And on the basis of that, then you can estimate what the magnitude of the buoyancy force is. So if you're swimming in very, very dense water that's slightly heavier, your buoyancy force is going to be a lot higher, so in salt water. But if you're in a pool, for example, where the density would be slightly lower, then you won't have as much of a buoyancy force. Okay. So buoyancy is important as well for body position and balance. Again, it's the first thing that you want to get right with someone who's new to swimming, is that you get your body position right. I always say that if you can float, you can swim. So if you can get your legs going as a beginner swimmer, if you can get your body position right as a beginner swimmer, everybody can kick, because it's a case of imitation. Even if it's a poor imitation, you'll still get moving through the water, and then the arm work kind of sets itself out, because it's the first thing that people see is how to move your arms through the water. So the body position is quite important, and that's kind of dictated by the muscle-fat ratio, usually, or the density of the swimmer. So everybody's body shape is slightly different. If you're carrying a few extra pounds and you've more fat, the density of fat is less, so you'll tend to float a little bit better. But if you're quite lean, the hardest people to teach swimming to are kind of the gym jockeys who'd spend a lot of time working out. They'll be quite muscular, but you have a hell of a time trying to get their legs up when they're initially trying to get control of that buoyancy and body position. So the volume of air in the lungs as well will affect your density for obvious reasons. It'll increase your volume and lower your overall density, and it'll make you float. So if you're a beginner swimmer, if you want to control your buoyancy, it's a case of controlling your breathing. You're inhaling and you're exhaling. And learning to sink in a controlled way is actually one of the best ways of getting someone to overcome their fear of water, because they can learn that if they sink nice and smoothly, they can get their feet on the bottom and they're stable quicker. So down is sometimes positive. And the water density, as I say, if you're a triathlete and you spend a lot of time swimming in the sea, well, you're going to be naturally higher in the water because the salt water has a higher density and your buoyancy force is higher. Okay. So drag then, drag is what we're always trying to eliminate. So particularly at kind of the competitive level and elite swimmers, there's a constant focus on drag. So you want to perfect your technique to minimize the different elements of drag. And if possible, then you want to use bodysuits to minimize skin friction drag. So there's three main types of drag that I would have looked at, say, as a swimming instructor. And the first of these would be profile drag. So that accounts for an awful lot of the resistance that you have when you're swimming. And drag is basically slowing you down. So if you see the swimmer on the left, so yeah, your left, my right. If you see that swimmer there, because their legs are quite low in the water, right, there's more contact point for that fluid flowing underneath them. So it slows them down a lot more. Now, if the legs were a little bit higher, they'd move easier through the water, okay? So the bottom line with this is the larger cross-sectional area you present to the oncoming water, the more drag that you're going to meet, okay? So if you're a lateral swimmer, if you've got a kind of a wide swing in your arms and you're moving a little bit from side to side, then your overall cross-section area is going to seem bigger as well, and that's going to create more drag. So you want to go straight and narrow, and streamlined is kind of the ideal position. So hands over the head down between the shoulders. And again, if you're a swimmer, you've been practicing that for a long time anyway. Okay, so that's the idea. It's to minimize profile drag. Skin drag. Right, so skin drag is the reason why this guy wouldn't make a great Olympic swimmer and why Michael Phelps and his colleagues would tend to shave down before races. Okay, so as the fluid is moving over the surface of your body, if that surface is rough, you're going to get more drag on your skin. It's essentially a form of friction to slow you down. So what you want to do is make that surface as smooth as possible just to ease that fluid flow over you. And so there's been a lot of focus on skin drag in the last few years, particularly with these high-tech suits that we'll look at in a minute. The next form of drag is wave drag. So where the fluid meets the air, where you have that boundary, if you have a body moving through that boundary, you're going to get a little bow wave in front. Everybody will be familiar with it, and that acts against you. Okay, so it's quite noticeable in breaststrokers or butterflies who might raise themselves high out of the water. You're going to get this intermittent wave drag pushing against you all the time. Now, if you swim in a streamlined position underneath the water at a particular depth, the wave drag becomes negligible. So on the push-off, the first phase, say, of your length, you're avoiding that wave drag altogether until you need to surface and you start meeting that boundary. Okay, so thrust. Thrust is the main thing we want to maximize. This is butterflies, and butterfly is a really explosive stroke. Okay, so you have a very strong propulsive phase at the end of it, and that's a really good example of kind of maximizing your thrust in a phase of the stroke. So there's two main components to this that I would have learned as an instructor, and that's the propulsive drag theory. So that's derived from Newton's third law. So every action has an equal and opposite reaction. Okay, so essentially what that says is your hand is like a paddle. As you start to pull through the water, what you're doing is you're creating a reaction force with the rest of your body that's pushing you through. So the position that your hand enters the water actually isn't too far off from where it exits, and your body is actually moving around your hand as you're swimming. Now, what they realized when they started the videotape elite swimmers, I think it was back in the 70s, they noticed that the hand wasn't moving in a linear pattern, it was moving in a curved linear pattern as they were pushing themselves through the water. And the reason behind the thinking behind that is that as you start to push on that water, right, you're imparting some energy to it, and it starts to get slippy, say, you don't get as much purchase on it, and so the reaction force reduces a little bit. So what you tend to do in swimming is scull a little bit, and you do these S-shaped sweeps to get the maximum amount of purchase on the water as you're swimming. So that's where that comes from, propulsive drag theory. The other principle then is Bernoulli's principle. So this is the same thing that gives lift to airplanes. So if you have a hydrofoil-shaped object, so like a swimmer's hand on its side, if you have fluid coming in at this direction, the fluid running over the top surface of the hand is going to speed up. There's a larger surface area to cover, and the static pressure that applies is going to reduce a little bit. On the bottom of the hand, fluid moving relatively slower, and you'll have a larger upward static pressure. So that gives you lift. Now you also have a drag force associated with that depending on the angle that you enter your hand at, and you call that the attack angle. So I suppose the main thing with this is there's a drag and a lift component to your hand entry and your sweeping movements as well. And in competitive swimming, you'd hear a lot of people talk about a good feel for the water. So really what they're getting is a really good balance between that lift and drag, and their pitch of their hand as they're pulling through the water is kind of optimized to give them as much propulsion as possible. Now there's a lot of debate as to how much the lift contributes to your propulsion and how much the drag does, and I think that some of the techniques that we're going to look at aim to answer that question. Okay, so swimming technology. So that's kind of the brass tacks. If you're a swimmer or coach, you would have been familiar with all of that stuff. I probably learned most of it from you. So what I'm going to talk about now is just a couple of examples of some engineering technologies that have been used in other areas and they're being applied to swimming. Again, it's not a really broad kind of cover of all of the latest engineering technologies. We just don't have time for that. So I just picked three in particular, and then I have a whole kind of load of gadgets at the end, just some snapshots of them that I can talk about as well. Okay, so we're starting to move more into the fluid dynamics and electronic side of things. Okay, so just a brief rundown of the major technical innovations in swimming. When I was doing up this, actually, I was looking for a similar innovation timeline with electronics, and what you'd see is around the 70s and 80s, the start of personal computers, mobile phones in the 90s, and then 2000, you have your smartphones and severely advanced technology, but very little carryover between the two timelines. Okay, so there has been a lot of innovation in swimming. It hasn't always been on, say, the electronic side of things. So in the early 1930s, I think the first swimming goggles in their current form kind of came out, and they were essentially aviator goggles with some form of putty on them to basically waterproof them so you could see under the water. 1933, swimming fins patent was granted. Now, the fins are probably around for a lot longer than that. In the 50s, then the Australians started to become very conscious of skin drag. So you had John Hendricks wore a silk swimsuit. It was a smoother surface so that he could reduce his drag. And you had Australians shave their bodies in the 1956 Olympics. So that's the first documented Olympics where they shaved down for it. And the University of Michigan then developed the electronic touch pads. So an awful lot of swimming meets, what you'll see is these black and yellow Omega pads generally on the end of the pool. I'm sure many of you have used them. And they'll just instantaneously get your time on impact. So you try to hit the pads as hard as you can. And that just eliminates kind of the human error associated with the manual timing. Electronic timing then was used extensively in 1972 Munich Games, and then kind of throughout what happened then in the 70s and 80s, which you had a lot of video analysis and for trying to understand the mechanics of swimming and the fluid dynamics of swimming. And there's a huge amount of research done on that, and it's kind of an integral part of swimming these days. I haven't covered it in this lecture because it's an absolutely massive field. So that was the 70s and 80s, and then kind of as you got into the 2000s then, say late 90s, 2000s, you started to see these high-tech swimsuits come out, and we're going to see a few of those actually next. So the first area I wanted to talk about was computational fluid dynamics. Okay, so I'm not a fluid dynamics expert, but this is kind of an emerging area. Over the last 10 years, there's been a lot of work done on this. And essentially, what fluid dynamics, computational fluid dynamics is, it's modeling movements of fluid around and over different surfaces in a flow model. So you have essentially what's a virtual tank. You put your swimmer inside in it, and you can analyze what are the pressures and forces and vortices being caused around those swimmers. And this has kind of been powered a lot by powerful computing. Computers are just getting faster and faster and faster, smaller and cheaper all the time. And that's enabled an awful lot of this because the equations used to model fluid dynamics are incredibly complex. So in order to make it practical, you need to have fairly severe computing power, which has kind of kicked in the last 10 years. So in 2002, a guy called Bixler, from 1996 to 2002, he was the first to really adapt computational fluid dynamics for kind of swimming applications. And what he had was a model of a swimmer's hand, and what he wanted to do was demonstrate the proof of concept. So he took something that was kind of known, that if your angle of attack is very severe, if you push against the water like this, you're going to get a huge amount of drag, right? That makes sense to everybody. And if you tilt your hand like this, your drag will be reduced. So that was the first thing that he looked at, was by varying the angle of attack, what was his computational model going to tell him about the drag and lift coefficients. So what he found was that the hand drag coefficient was at a minimum at an angle of attack of 0 degrees and 180 degrees. Okay, so drag was minimum when the hand was like this, and then it peaked at 90 degrees. All right, that's, every swimmer, I think, from the day they start would know that. You'd realize that. It's the same as when you put your hand outside the window of a car, moving car. I wouldn't recommend it, but you can feel the same thing. You can feel the drag on your hand. And what he found, again, which was interesting, was that the lift forces were at a minimum at 95 degrees and peaked at 55 and 140 degrees. Okay, so again, that makes sense. Now, adapting that information into your swimming technique, where you've got a swimmer's arm is rotating and moving all of the time, is a little trickier. All right, so this was really a proof of concept. And the important thing about this was the arm is static, so it's a fixed model of the hand, and what you do is you model the fluid around that. So a lot of work then was done kind of throughout the 2000s, the noughties, up until 2010, on various aspects of it and refining different models. So this is just an example of one study that was done, a turbulence model, and this was done by a researcher called Zaidi in the University of Rouen in France. And what they were looking at was an ideal turbulence model. So you have to plug in certain values into your fluid dynamics model. And they basically came up with a very good turbulence model to predict profile drag and skin friction drag in a streamlined swimmer. So they took a national level swimmer at their institute, and they scanned her with a 3D scanner. I think it was Konica Minolta, I think, have them. And then they were able to plug that model into their fluid dynamic model. So they took a real scan of a swimmer, popped it in, and they looked at different drag coefficients then as a result of her body shape, and then this turbulence model that they developed. And they were also able to measure it in a flume. They popped her in a flume, and they were able to compare the CFD results with their measured results. And what they found is, again, it's something that's been well known in swimming for a while, is that skin friction drag has a smaller effect than the profile drag. But as you become kind of a competitive Olympic level swimmer, there becomes less and less you can really do about your profile drag. Whereas a skin friction drag, you can have a big impact if you alter your suit or slight subtle changes in your body position. So a follow-on study from that was a guy called Pope. This is the same group, same university, in the University of Rouen. They had a male swimmer, and they wanted to look at static pressures and shear stress around a streamlined swimmer. So it's the same body position, and they're modelling these swimmers at a meter, typically a meter under the water, right? So it's a little bit deep for streamlined position. And it's to eliminate wave drag from all of their calculations. So we were saying that there was profile, skin friction, and wave drag with the three types. Well, if you look at just a streamlined position on a static model, it just makes the computation so much easier. So they looked at 3 different velocities and 3 separate head positions. And what they found was that, again, it's something that from day one, if you start swimming, if you lift your head while you're kicking your legs from a streamlined position, you're going to catch more water than if your head is down between your arms. And if you drop it a little bit lower, you're going to catch more water. But they got very subtle changes in head position, manifesting as big changes in static pressures and shear stress, right, on the head and around the shoulders. And what it did is it changed the flows over the shoulders as well on their computational model. So this paper is actually very, very good. There's a lot of these really good sort of heat maps that will demonstrate all of the hot spots in terms of build up of pressure and potential areas where there's an awful lot of drag. So they started to have a lot of practical outputs from these CFD models in around kind of 2006, 2007, and Speedo had been using them to develop their next generation of swimming suits, which are the laser racers, which you can see here. So I suppose the computational fluid dynamic pros is that it allows complex modeling and imaging of forces for static body positions. So as yet, there has to be a good bit of work done on getting, a perfectly moving, animated virtual swimmer flowing in these complex fluid pools. But it's definitely a very, very good start. It can approximate what we currently can't measure or what you need NASA really to measure a lot of the time. Okay, so it's cheap in that respect. And it's becoming increasingly accessible as computing power is increasing. So there's a huge amount of expertise actually in this university, not coming from me by any means, but we have a few people working on this for a couple of biomedical applications. So arterial flow and that type of thing, there's an awful lot of work being done, and it's not a huge leap to translate it kind of into the swimming domain. Okay, so there's expertise locally, and I think there's a lot of interest in it. So the limitations of it is complex, right? So it is, to some extent, it's kind of high level research stuff that's going on at the moment, and it's difficult to model dynamic forces. But essentially what's going to happen is you're going to be able to get a 3D scanner for your swimmers, and you're going to get a package that's going to do a lot of the analysis for you. That's maybe 2-3 years away. And it's currently limited for the output from it is kind of limited in terms of training or coaching. I mean, people know that you're going to get a lot of drag if you turn your hand on your side, and they know that if you raise your head in a streamlined position, it's going to create more drag. But the subtleties for Olympic swimmers are really, really important. So it's the degree of drag and the pockets and the vortices that are created when you make very, very subtle changes to your stroke. That's where it starts to become important. The other thing as well is at higher velocities, drag increases, right? So the people who are swimming the fastest are impacted most by drag. So for Olympic level guys, this stuff has started to reap a lot of benefits. So that's the Speedo's Laser Racer. So it came out in 2008, and I have a video here actually on the work that went into it, and it's kind of a practical outcome from the CFD stuff. So I hope we sound. If not, I'll do a voiceover.
Meet the new spacesuit from Speedo, the Laser Racer, an ultrasonically welded, ultra-low friction suit that actually repels water. Developed by top scientists from around the world, the suit's fabric was tested at NASA.
So that's a flume that you do a lot of your measurements in.
Aerodynamic qualities of space shuttles.
We're very privileged to be working with NASA. NASA obviously spend a lot of time working out the design of spacecraft and aircraft and how they can reduce friction on those vehicles. And we work with NASA in the same way to work out how we can reduce the level of skin friction drag created by a swimmer in a suit moving through the water.
The result is what experts claim to be the fastest swimsuit in the world.
In a traditional suit, there's a lot of skin movement. It just moves all over the place. So what these new suits are doing is actually controlling a lot of that extra movement. So it, again, keeps the water flow a lot closer to the body, makes it much more streamlined, so you move through the water a lot more cleanly.
Athletes wearing the Laser Racer therefore need less oxygen, meaning they can swim faster for longer. By scanning more than 400 elite athletes from around the world, Speedo's researchers were able to identify the areas on a swimmer's body.
So what they did, I think the audio is dropping in and out, is they scanned, I think, 400 swimmers, Olympic level swimmers, to get a model, an ideal model for their say, phantom swimmer that they did a lot of the computational modeling on.
I felt like a rocket, right when I hit the water, I felt like a rocket. So I felt unreal, and can't wait to race in it.
I know Speedo puts so much time and effort and energy into developing the best suits, and knowing that they're getting scientists from all over the world and people from NASA, I mean, how can you question that it's the best suit?
When people see all these great athletes lining up behind the blocks and with these great physiques, these futuristic looking suits on, it adds to the sport, it adds a new dimension to the sport, and I think that's exciting within itself.
The results have seen skin friction drag reduced by 24% compared to the Speedo suit worn in Athens in 2004, leading experts and swimmers to claim they are confident that more medals will be won and more world records broken by Speedo athletes this year than ever before.
Okay, so the main thing with those suits, with the Laser Racers that came out, was that they noticed that there was a lot of frictional drag on the front, right? So you can see here, so what they did is they inserted these very smooth panels to make that surface very, very smooth, and to, well, the marketing material would say to repel the water away from the swimmer, okay? So they were just minimizing the frictional drag as they went along. The other thing they did is they made the suits actually quite buoyant and also very compressive. So you get less vibration on the surface of the swimmer's skin, and also they'd swim a little bit higher in the water. The problem with it was that in the 2008 Olympics, I think 92% of records that were broken or medals that were won by swimmers swimming in these suits. And the International Federation for Swimming went, what the hell is happening? This is starting to become a serious problem. It's not leveling the playing field. If someone has a suit, they have an advantage over somebody else because it reduced the drag so much. So in 2010 then, FINA came out with a statement saying that there are specific types of swimsuits that are appropriate for Olympic levels, and I think it basically disqualified the laser suit from future Olympics. So it'll be interesting to see this time round, will there be as many records broken this summer as were in 2008. Okay, so the next thing I wanted to talk about was the digital particle image velocimetry. Okay, so I'm just going to be kind of brief on this. This is sort of an exotic technique that's been used in zoology actually for a long time to study things like, I don't know if you can see these vortices here beneath the hummingbird, and to understand how different animals move through, say, fluids and gases. And what's happened in the last kind of 6 or 7 years is that researchers from New York, I think it's one of the universities in New York, a guy called Professor Timothy Way, basically was able to scale up one of these systems. They're normally very, very small to use on swimmers in the US swimming team. So the normal experimental setup for this, you'd have a tank of water, fluid, say in this case. It can be a gas as well, and that has seeding particles inside in it. Okay, so they're suspended in the water. You have a laser then that's processed through some laser sheet optics, right, that essentially creates a very, very thin blade of light that cuts through that tank. And then you have a camera that will image that light, which will reflect off the particles and bounce back onto the camera. So the movement of the particles, these really, really fine particles, can be tracked. So if you move the fluid, then the particles move, in the direction of the fluid, and you can quantify the magnitude and direction of that particle movement. And it's all done then using kind of fairly intensive computational processing. Okay, so again, it's an exotic technique at the moment from swimming, and it's very much in the research domain, but there's been some very interesting outputs from it. So this is an Olympic breaststroker. That's Megan Jendrick. I think she was a medal winner in 2000. She swam in 2008 as well. And what they basically had a larger setup. So they had Megan swim in a large tank, and instead of using laser light, which would have blinded her, and normal seeding particles, they used large floodlights and micro bubbles that were floating up from the bottom, and she was swimming in a particular plane. So if you can imagine that, the image actually, the particle flow represents a slice kind of through her midline as opposed to through her shoulder. And what you see here are very small arrows on the side, right? The direction of the arrow obviously indicates the direction of flow, and the magnitude then, say from blue through to red, indicates the magnitude of that flow, so the velocity of it. Now there's videos available for this of Megan swimming, but they're quite poor quality, and actually there's no research results published on that series of study that they did with the US team, so I reckon that they're probably sitting on it. They did it in the lead up to the 2008 Olympics, and there was a huge amount of work and kind of press around it, but none of the results were made publicly available, I suppose, and part of it could have been a competitive advantage, or it may not have worked out as well as they had hoped. But there's a very good video of a dolphin. There's this paradox in zoology called Gray's paradox, right? So this guy Gray proposed that a dolphin couldn't possibly have the strength to propel itself as fast through the water as it seems to do, and they were always trying to figure out how was that the case. And measuring the force of the fin, the force coming off the fin of a dolphin, was always a big problem for them. So they took this experimental setup that they'd used on the US swim team, and they took it down to US Navy tank, where they had retired bottlenose dolphins. Now, I don't know what kind of service the bottlenose dolphins put to use in the Navy, but they had a group of retired dolphins, and they trained them to swim straight through this field, this light field, using a similar setup. So you have a floodlight and micro bubbles coming through, and it's a good example of how you can visualize. I mean, this is as real time as you'll get. As the dolphin's swimming through the water, you can see all the different flow patterns that are going on, and you can kind of pinpoint areas where drag might be created. So the dolphin's going to enter from the left and kind of swim out, and if you just keep an eye on the tail and see the flow patterns around it. Okay, so you'll see a hand waving the dolphin in the right direction, and then the dolphin swims in. And you start to get this vortex. So what they were able to do was they were able to measure the forces based on that vortex flow. And what they found was that a dolphin is able to produce more than enough energy to swim as fast as it did. And it kind of put that question of Gray's paradox, which had been around for, I think, decades at least, to bed. So I suppose the point about that is that being able to visualize it as your swimmer, say your breaststroker in that case is swimming, is incredibly powerful, right? And being able to make adjustments and then revisualize it and quantify it is essential. So that's a really big setup at the moment, right? That's kind of a first stab prototype, I would say. But as time goes on, I mean, if the US team found that was pretty beneficial, we may see more of those in the future, but that's early research stuff. Okay, so this is more an area that I'm kind of very familiar with in terms of the work that we do in our own universities, or our own research group rather. It's kinematic sensing. So kinematic sensing is just measuring human movement, right? And there's a number of ways that you can do it. As I mentioned before, traditionally in swimming, you'd use video analysis to look at stroke mechanics, and that's been around for a long time. What's happened now is that I'm sure you're all familiar with accelerometers on your smartphones, right? When you turn your phone on its side, the screen will adjust and tilt for you, okay? So these sensors, essentially, they pick up acceleration, tilt, and rotation, and they're tiny. They're cheap and they're readily available. Okay, they're in almost every smartphone you have now. The Wiimote is a very good example. So that has a couple of different sensors inside in it that will be able to detect the orientation and rotation. So for a swimmer, this is hugely beneficial because you can put these things on any part of the swimmer's body and you can look at arm mechanics, rotation, speeds, acceleration, and you can have as many of them as you need. Within reason, but it is feasible to have a bodysuit with these devices in it. So I'm just going to talk about some of the work that's been done kind of for land-based activities, which has kind of exploded in the last 2 or 3 years, and then look at ways that can be adapted for swimmers. So I think this is a massive leap for swimming. Okay, so there's a couple of commercial kinematic sensors, right? And these would be used, so if you're looking at medical applications, right, measuring physical activity is really, really important. It's kind of a determinant of someone's overall well-being, and almost in any area or any illness you're looking at, physical activity has a bearing, okay? So also in fitness applications, if you're doing a lot of training yourself and you want an automated way of logging runs or cycles, you have a whole host of devices now that can do that for you. So Garmin have a few of them. Here are a couple of different kind of categories of devices. On the far left, you've got a shimmer kinematic sensor, right? I think that's their standard unit. So it has a gyroscope and accelerometer in it. It can do some wireless transmission, and it's a data logger as well. So it'll record every movement once you tell it to. And we have a lot of these in the lab. A few of the lads have developed a lot of expertise at working with these. And our sports and exercise engineering students will go on placement. Shimmer are based in Dublin, so they'd spend a lot of time actually developing applications and working with the company to come up with different tools and applications for this. Okay, so that's kind of a research grade. I think that's about €200, I think, for the unit. And then there's a couple of bells and whistles you need on top of that. In the middle you have a Fitbit, so that's like a consumer level pedometer. So that's got an accelerometer. It'll measure changes in the acceleration of your hip and be able to detect how many steps you're taking or how active you are. And they're really, really common. So in MedGadget, which is an online journal, basically, that we cover an awful lot of medical devices with that. And in the last year, we've seen a huge amount of these devices come out. I mean, I'd say there's probably 20 or 30 new devices that do the same thing. And it's basically about quantifying your levels of activity, and it's absolutely massive. So Shane Lowe had a talk on it actually earlier in the seminar series. And they're just, if you throw a stone, you'll hit a new one of these devices. I mean, they're really, really common. And on the far end then we have the ZAMZ, right? So this is a physical activity monitor for kids. It's designed like a USB stick. And the more active they are, the more points they log up, okay? So if your kid spends all day jumping up and down in the bed, right, they're going to get huge points because the accelerometer is going to go crazy inside in it. And they can plug that into their laptop then, connect through a website, and it'll give them rewards, discounts for things like clothes and sports accessories and that type of thing. So what you're seeing is, a research level device come into a kind of a trendy consumer level quantifying device, and then you have that data being used to kind of socialize your fitness, right? So it's better, the more points you have, you start to compete with other kids who have their ZAMZ device, and you get rewards then based on it, okay? So that social element is starting to appear. The problem is that this really hasn't hit the pool yet. There's 1 or 2 devices that are starting to come out, but there's really no good reason for it. I mean, if you waterproof some of these devices and you kind of adjust some of the algorithms that are in them, they can be excellent stroke monitors, and they're incredibly cheap and they're readily available. So this is an example of like prototype kinematic sensor for swimming, and I think it was developed by a research group, I think 3 or 4 years ago. You'll see a lot of these, and there's a lot of research on these in the last few years. So you have an electronic prototype worn on the wrist, right? So as it's on the wrist, as you're going through your stroke movements, it's picking up acceleration and velocity data and rotation information as well. And what you get is, say, you get information back like this, right? So this is the change in acceleration in one axis of the device. So as the swimmer is going through each consecutive stroke, these dotted lines represent one stroke cycle. Okay, so you get a peak in acceleration, you get another peak in acceleration at the bottom, but it's in the opposite direction. So you can measure stroke rate and the time as well. All of these devices would have real-time clocks in them, so you're measuring time as you go. And then you can get your stroke length, because the tumble turn can be detected because it's a full body rotation. Okay, so that'll automatically, when you finish your length or your session, you can get your stroke rate, times, stroke length, splits at every stage of your swim, and that's really, really important, useful data. So over a 400-meter swim, at the end of it, by how much does your stroke length start to decrease as you start to fatigue, and what can you start doing about that? So having that information is critical. Having it in real time and having it fed back to you is even more critical, I think, because you're in a position to do something about it when you're in your training session. So those are really, really powerful devices. And there's two kind of main consumer ones that are, well, this is the big one actually, the SwimSense. So I think that's commercially available here now. It's essentially the same thing in kind of a watch format. And a crowd called Finnis make this. So Finnis kind of are the swimming technology company. If you're looking for a swimming gadget, Finnis usually have their name stamped on it. The problem is that they're not always the highest grade stuff, so they're kind of designed to fail. A lot of the time, I got a pacer that lasted me 3 months, and it just beeps. You put it under your hat and it beeps, and it lasted 3 months. And it just makes sense, I suppose, from a business point of view, it makes sense that you'll have someone come back in 3 months' time and buy something new. But the SwimSense I haven't used myself, so I hear it's quite good. And it's an accelerometer in your wrist. It'll give you stroke length, stroke rate. It'll give you your splits, over however many distances. And I think there's an upload feature as well, so you can log and graph all of that on the web. I'm pretty sure you can post it online as well. So it'll be like Map My Run, right? So when you finish your run, you post that you did a run, you did it in a certain amount of time, and somebody else can view it, right? So kind of that socializing swimming and socializing fitness can actually be quite good if you're someone who finds it hard to get a good session going in the pool by yourself. If you're doing sessions with somebody else and you can compare, right, that's quite a useful incentive. The other thing I saw that was very useful for coaching, again, it's based on kind of this kinematic technology, is there's a crowd called Avida Sports in the US. And this year they've started to trial, it's basically a kind of a suite of accelerometers. You have 4 accelerometers that you wear at the end of each of your limbs. So you have on your wrists and your ankles, you'd have one of these devices. And it'll pick up stroke rate for every arm. It'll be a little bit more specific. It can get your kick rate and kick intensity. And I think that they've got a heart rate feature as well. So those devices are all wired to kind of a terminal that sits underneath your hat, right, that's up out of the water. And as you're swimming along, that sensor data is being transmitted to an antenna system on the side of the pool that's connected to like iPads that your coach has. So as you're swimming in real time, your coach is looking at what your stroke metrics are and volumes of it. I mean, you've got lists and lists of data that these devices are generating. I think the clever thing about this really was overcoming the wireless part, right? Because if you're wirelessly transmitting data in water, it's tricky if you've got a lot of data to send. If it's in a water and an air medium, it can be even trickier. But what they do is essentially, when the head is clear of the water, they'll send off information, right? But when you're under the water, you basically need to wait until the swimmer pops up. But it's very, very clever, and I think that a lot of universities are picking up in these systems. Kind of well-funded swimming communities in the States are starting to test out these systems, and I know the University of Michigan has one installed. So they're really impressive. I'd recommend hopping onto their website actually, because they have a few good videos and you can see the stuff they do. And if they deliver on all the things that they say they do, I think that's pretty revolutionary for coaching. I think the SwimSense, if you're kind of a solo swimmer and a triathlete, right, having GPS might be handy because you might be able to see your deviation if you're an open water swimmer over long distances. The SwimSense might be more on that end of things. So there's an awful lot of research done, and you literally just have to Google accelerometers and swimming and a load of stuff will pop up. There was an Australian researcher called Neil Davey who did his PhD on this area. I think he was one of the first to kind of publish a very sensitive accelerometer-based system that's worn on the small of your back. Okay, so it could pick up roll and rotation from a swimmer, and then stroke lengths. And he started combining them with other acceleration data. But if you're an engineer, his thesis is published online, so all the information is there. So I'd recommend that, you know, if you have an interest in it and you're kind of an electronics enthusiast, there's no reason why you can't put one of these systems together, you know, in a matter of months. They're pretty quick to prototype. An awful lot of the information is available online, and there's huge amounts that you can do with it. They're only kind of scratching the tip of the potential of these kinematic sensors. So just to finish up, there's just a few gadgets that I thought would be interesting that I kind of would have come across through MedGadget and then just browsing, I suppose. Up in the top left corner there, you can see that's the Swim P3. So I don't know, that's been available for a while, right? It's basically an underwater MP3 player, and the problem with MP3 players underwater is, one, electronics and water generally don't mix, as a kind of general rule of thumb. You wouldn't bring your phone in the pool. But the other thing as well is that if you have earbuds in, right, the sound doesn't travel through well, in that gap where you're getting water coming in and out of your ear. So what they have, it's essentially its bone conduction system. So it sits on your ear and rests on your bone there, and it creates vibrations that are supposed to reproduce, the songs that you're listening to. I hear it's quite good. I haven't used it myself. So on the right, on the top right, that's the Aqua Pulse. So that's a heart rate monitor. That's an underwater heart rate monitor, and it uses pulse oximetry, I think, just to pick up changes in heart rate. Okay, so again, that clips on your ear, and there's a little sensor clip then that will go on your earlobe. And as you're swimming along, then it'll beep, or it will verbally tell you what your heart rate is at a given instant time. So that's really good for training. I mean, they're really common for running devices now. You can see at any time what your heart rate is, but getting the real-time feedback is usually a bit of a challenge. In the bottom right-hand corner, that's actually a prosthetic fin. So I thought that was actually quite neat. That kind of straddled the medical and swimming technology side of things, right? So we're all familiar with the Blade Runner, right? The prosthetic leg that can, I don't know what his name is, South African runner. So I thought this was kind of the swimming equivalent, right? So this just goes on your leg, if you're an amputee, and will propel you to the water pretty quickly. And I thought it was just a neat design. There's kind of a goggle LCD feedback. So this is a concept, right, in the bottom corner there. So a big problem, right, when you're swimming is that if you're getting all these metrics, what are you going to do about it? Hearing it and hearing bits and pieces of information is great, but ideally you'd like to be able to see it, and you'd like to be able to see your levels increase as you're going along. So that's a concept. There's a lot of these goggle concepts out, and the technology is probably there. I think it's just the interest and the funding for it is going to take a little bit longer. But there's challenges with the optics, with putting a display that close to your eye. And in the middle we have a prototype visual feedback device, which is essentially some waterproofed LEDs inserted into a regular goggle, and that has a heart rate sensor built into it as well. So you get feedback basically on your heart rate as you're swimming along. And that was just developed this year, I think. So these are kind of far out swimming devices. How practical they'll be kind of is a big question. On the top left-hand corner there, that's a device for measuring VO2 max. So that's a really important kind of physiological measure when you're swimming in terms of peak performance. And it's a gas analyzer, right, that attaches to the mouth to kind of a suction mask, and it's quite big and bulky. So it's really awkward to swim with. And it has tubes that have to go all the way back to the deck to the gas analyzer, so you can get some information back on it. But you can do it while you're swimming, which is the advantage. You don't have to simulate swimming out of the water. The problem is that you need to rig up, you need to have your pool basically completely rigged up to handle all the tubes and that whole system. There's a company in Italy that manage that. They do an awful lot of kind of respiratory devices for medical applications and exercise testing. On the other side then, what you have, that small cylinder, is a Bion microstimulator, right? So that's used for medical applications. It's an injectable muscle stimulator that's used for, say, people who are paralyzed, spinal lesions. And that can be injected close to a nerve. It requires a very little amount of energy, and it has a battery in it, and it can be recharged wirelessly using a cuff to stimulate different muscles, so to kind of restore function in people who've lost some nerve function. Now those Bions also have, essentially it's a microcomputer in a titanium casing. So there's a huge amount of sophistication in that tiny little package, right? So they have EMG sensors for that, so they can detect muscle movement. But you could easily put pH sensors in there as well. There's an awful lot that you can do. It's essentially a very, very small implantable microcomputer, and it can be used as a sensing interface maybe down the line. Now, to justify injecting yourself with that, you'd really, really want to be stuck. But it's just an example, I think, of the way the technology is going. I mean, these are already implanted in a few people in Sheffield for rehabilitation applications and that. So they're that's current, and that's been out a few years. On the bottom left-hand corner, then, that's an advanced tactile device, right? So you have a pressure membrane there in blue. It's an artificial hand or an artificial skin, and you have a pressure membrane there that's filled with fluid, and that's coupled to a pressure transducer. So what that does is, as you move a finger, say on a robotic hand, as you move that finger over a surface, it'll generate acoustic waves within that pressure membrane that can then be decoded, and the texture can be detected, right? So it's an ultrafine pressure sensor. There's a lot of different types of pressure sensors that you could use, but it could be very useful for examining, say forces on the hand and optimal sculling patterns in a swimmer. And I think there've probably been a few studies done on that. Pressure sensors are fairly widely available, but that's the latest in that technology. On the very top, the poor old lab rat there has a fibre optic cable implanted in the ear, right? And the light going through that cable changes depending on his glucose levels. So it's research that's been done for diabetics. And as your glucose levels start to get out of control, that light will change colour. It changes the refractive index on the coating of the fibre that's implanted. And the beauty of that is you can inject that in and pull that out. Requires no surgery. So they can make those responsive to a whole load of kind of biochemical processes. So things like pH and all the rest. So I think well down the line, if it ever happened, I just imagine a coach standing on the side of the pool looking at all these glowing swimmers and knowing who's kind of dragging ass and who needs to pick it up. So that's futuristic stuff. This guy really has no major application for swimming, but I thought I'd include it. It's a water-propelled jetpack, right? So there's a kind of an impeller under the water that shoots water up through these tubes and out the jetpack out the back, and it was developed by an extreme jet skier. And there's a company manufacturing these in the States. I think it came out a year or two ago. It's kind of crazy, but the videos actually are very good if you ever the YouTube hit, if you ever get to see it. So. All right, so what are the conclusions? Well, I just covered a couple of areas, right? So my main point, I suppose, is that swimming is incredibly popular in this country. I mean, I'm probably preaching the converted here because I recognize a lot of swimmers, but it's massively popular. The kind of collective health benefit of it is huge for our economy and for our healthcare system. You know, if you can get everybody in the pool, well, then you're saving a lot of problems down the line. It's beneficial, and it's also a great spectator sport, which I think sometimes isn't taken advantage of. I think if you spend weekends at a gala and a competition swimming, you realise it. But I would just love to see kind of these mass swimming spectator events at some point down the line. So that's just pushing my own agenda. But there are a number of basic physical properties which dictate effective swimming, and they're easily learned and used as a swimmer. So that's more for the engineer who's maybe thinking about getting into swimming, right? There's a couple of simple principles to bear in mind when you're doing anything with swimming. And we cover those. I mean, there's four main forces, and you want to keep an eye on those. I suppose really with the technology now, like a lot of things, right, everything is about data, and data is power. So swimming is becoming really quantified and really precise. These kinematic sensors are incredibly precise. And, it's only a matter of time before we're strapping on suits, even for your own personal use, to try and refine your stroke characteristics. And you're not going on feel alone and what your coach is telling you from the side, which is still crucial. But, if he's not there, then you need to be in the water and need to be getting some sort of feedback yourself. Because the hardest thing I find when I try to train by myself is that I just have no idea how I'm doing. So swimming is becoming more quantified, and I think that's going to drive it an awful lot. And it's going to drive coaching programs and understanding of the sport. And I think we really need to embrace a lot of that. I mean, there's a lot of expertise here, and we'll hopefully be educating our sports and exercise engineers to kind of come out with these types of devices and develop these applications. And we'd love if you were interested in kind of taking advantage of that. So that's it, really. If there's any questions, I'd be happy to answer them.
Okay, thanks very much, Gavin. Is there any questions? Open it up to the floor. I know we're kind of short on time, so we'll keep it brief enough.
Yeah, it's just hard.
1 second, do you have a? Oh, you got it.
It's hard to know where, say, at the Olympic level swimming, where it's going to go now because of the swimming suits banned.
Yeah.
This digital particle image thing you're talking about, is that the next?
It's not, it's been around for a while. There's a lot of refining to do on it, right? And again, I'm not a fluid dynamics expert. If you talk to somebody maybe from the Marine Institute, right, they're probably looking at this stuff day in, day out. But, I mean, my impression of it is that you're essentially, when you do your modelling, right, and the modelling is fantastic, you can validate an awful lot of that with the right digital particle imaging velocimetry. You can start validating a lot of those models. And the beauty of a model is that you can adjust different parameters as much as possible. And I think that kind of level of detail, I mean, as swimming gets gets more and more competitive and the times get tighter and tighter, that level of detail and the time spent on that level of detail is going to increase. And I think that's probably going to inform a lot of that. I mean, that'd be my take on it. This seems to be the best imaging technique at the moment for flow patterns around the swimmer while they're swimming. And I think that has an awful lot to do on the high end, definitely on the Olympic end. I think for kind of, national level, regional level, not so much. It's just too much. But yeah, I think that's probably going to start pushing things a little bit more. But it'd be great to see more results published on it.
Yeah, because back to the textile suits again from the laser, all those world records stand still.
Yeah, no, that's it.
There's only been one, I think, broken.
Yeah, that's it, and it's going to be a big challenge. But Mark Spitz had his records for how long? What I think is great actually, he swam in a mustache when he did that. Kind of skin friction out the window. Yeah. So you look at that and you think, well, at the time everybody thought, well, Jesus, this is never going to knock it down. But things are moving along all the time, and I think there's so much interest in swimming, and it is such a really tightly competitive sport that there is always going to be innovation around it, I think. And those athletes, Michael Phelps is a machine. They're just going to push themselves and push themselves and push themselves, I think, and you will see it. But it might stagger it for a while. So this year will be very interesting to see, I think. Yeah.
Thank you very much. Is there any questions?
First, I'd say it was a brilliant talk, right from the basic physics up to the more complicated fluid dynamic stuff. It was just massively informative.
Thanks.
And kind of a more engineering question I had. I was kind of expecting and surprised that there was no suits that would quantify the drag, nothing with force sensors kind of built into it.
What they do is, because I bypass a lot of the video stuff that's there, right? So they have a couple of ways of quantifying drag and visualizing it. So these vector arrows that you'd see in the DPIV techniques, right? So what they do is they have these kind of little cotton wisps that come down, and they're highly luminous. So traditionally, right, you have a suit with a lot of these hanging off it, and you have a swimmer do this streamlined position, and you could visualize, you'd get a rough idea of the drag, right, because those little wisps were being pulled, right? So you'd see a lot of that. But in terms of kind of electronic metrics, right, not so much for quantifying, very complex drag and kind of fluid dynamics. It's very, 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 very tricky thing to measure. You need a huge amount of instrumentation. And the problem is that as soon as you start loading instrumentation on a swimmer, you completely change the fluid dynamics anyway. So, technology is getting smaller all the time, right? So eventually it's going to get to a point, we had a microstimulator there that's smaller than a grain of rice. It'll get to the point where you can start putting some of these devices, maybe an array of them on. At the moment, they're kind of prohibitively expensive, I would say. But the video techniques are there. There are special suits that you can wear, but not in terms of the electronics end of it. Not really, not yet, anyway.
Is there any research in the area of swimming, say, on muscle activation?
There's a huge amount. It's a massive field of research, actually. The kind of physiology and the EMG studies. Actually, the EMG thing was interesting. A lot of the studies that I saw, right, are dry land, so they have a swimming bench and they get them to replicate a lot of it. Because the problem, again, with the EMG instrumentation is that it's underwater. Now, I came across 2 or 3 different companies that have some EMG sensors that will be, they're worn in the water, and they can give you some feedback. I think there was some work done in the Czech Republic 2 years ago. A guy had a prototype system, and he did some EMG studies. But generally, dryland studies is, as far as I'm aware, I'm not.
The kind of new EMG is mechanomyogram, and I'm just wondering, is there any which is measuring muscle activation by the actual acceleration of the actual muscle itself? Is there any research have you come across in that area?
I haven't actually, and maybe the kinematic sensors that were there, would enable that. You'd know as much, Alan. If you can do it with an accelerometer on land, you can do it in the water. That's my kind of attitude. You might not get real time as much as you'd like, but you'll get the feedback. So that's certainly a possibility. Especially like these. This is the inside of one of the devices, right? So they're really, really fine. The cases can be made a lot smaller, and this could probably be halved in size. So if you imagine an array of those all over the body, it's totally feasible. Yeah.
I think we'll take one more question if there is one. Okay, once again, I'd like to say thank you very much to Gavin Corley. That was a fantastic talk. Thank you. And thank you all for coming. Okay, take care.